Okay, so this lesson is just going to be a little one-day one. You guys have an assignment that's due tomorrow. It's not super short, but it's not very long either. It's just a review of some previous concepts. I think we definitely haven't seen enough graphs of the exponential and logarithmic functions yet. We've seen them, but we haven't seen them very much. So we should have these embedded in our minds. Okay, so we're going to do each one of these with transformations. So that's the theme of this, is the main theme of our class. In fact, the biggest theme is library of functions and how to transform different types of graphs. So remember, what's the main idea? If something is outside and it's a transformation, what kind of transformation is it? If it's outside? It's a vertical type, yeah. And is it going to be, if it's inside, then that means it's horizontal. What else do we know about it if it's outside what the function's doing? It's what it seems like. It's going to be pretty much what we expect. If we expect it to go up, it's going to go up, and so forth. And if it's inside, what else do we know? It's not what we expect. It's going to be opposite. So that's the guiding principle, remember, that we use when we do these. There's 3 graphs that we should keep in mind as well. These should be in the front of your library of functions, in the very front of your notebook if they aren't already. There's 3 graphs, 3 basic pictures that we should have in mind, yeah? Exponential growth, you guys all need to draw with your finger for me what exponential growth looks like.
Wait, what?
Right? From the asymptote up. So, like this. Usually it's going to be 1 above. Exponential decay looks like from there down to the asymptote, right? So draw that with your finger. And if you don't have any transformations, it gets also 1 above. And what's the logarithm shape look like? We've used that less so far, but we use it more today. It doesn't have a horizontal asymptote, it has a vertical one right here, and it goes like this, and it goes through 1 on the x-axis. Okay, those are the 3 shapes we're going to be using today when we transform. You should have those all in your head. Okay, this first function, I called it h. It's exponential growth, of course, right? Because it's base 2. Plus 7. What's plus 7 do to it? It's up 7. That's outside. What we expect is up 7. There's a negative. Where's that negative? Inside or outside? It's inside. Inside's horizontal or vertical?
So it will be right.
Inside's horizontal, so it's going to go like this. Okay, so we're going to take that shape of exponential growth we had a second ago. We're going to flip it, or reflect it. I'm going to say horizontally. The book won't say it that way. They're going to say like something like over the y-axis. Okay. Some problems in the book, just a couple of them ask you to do a table. I do kind of want you to do a table. You don't have to make it extensive, but just so you have a few points for reference. Okay. So let's do a quick little table on this one, just as an example. So let's plug some values in. But basically, I mean, we really don't need the table to know what this looks like in general. So we go exponential growth shape. Up 7 means 1, 2, 3, 4, 5, 6, 7. There's my new asymptote. Instead of being like that, it's going to be something like, erase these parts now. Something like this. Let's see if I get some points for that. So I'm just going to pick some simple values like -2 and such. So if I put 0 in, it's good to try to do these in your head. You can use your calculator, you can use scratch paper, but mental exercise is important. So if I put 0 in right there, anything to 0 power is 1. Plus 7 is 6. Does that look like it's 8? Yep. For exponentials, unless you do some kinds of transformations, it should be 1 above the asymptote every time. Okay, if I put in 1, that's 2 to the -1, which is 1/2. 1/2 plus 7 is 7.5. If I put in 2, 2 to the -2 power is 1/4 plus 7. Like I said, if you need to write these out, good, but you should be to the point where you can start putting these in your head. That's important to try to do. Negative, negative is positive, so that means 2 plus 7 is 9. Negative times negative is positive. 2 squared is 4 plus 7 is 11. Let's make sure this makes sense with the shape. So negative 1 is supposed to be, oh sorry, negative 1 is 9. Yeah, I think mine needs to be a little steeper. And at negative 2 it's 11. Pretty good. Yeah, you guys get the point. I think those match up to the graph. Okay, let's do another one. So we won't do a table on every one today. If it says in your directions, though, do one. Okay, so we got that one. Beta. You guys tell me, where's it been transformed? This.
It's down 6.
It's down 6. This. It's inside, right? Inside is horizontal. This is inside or outside? Outside. The inside is right there on this guy. So that's outside. That means it's vertical. Like that. So this is a reflection or a flip. If you want to say down, if you want to say across the x-axis, I don't care how you say it. Just say it somehow. Right. So just to save time, I'm not going to graph this one with a table. Alright, so asymptote, because this is exponential growth or decay, if it's e. Growth, because we should know that number e. If you don't already from the lesson last Thursday when I was gone, e is what number? 2.718.
170.
You're close. Very nice. Good try. Yes, you should know that number. Just like pi, it's just as common as pi in every class after this one. Pi and intervals, so very common. So let's see. 1, 2, 3, 4, 5, 6. Label my asymptote. Exponential growth would look like this, except it's been flipped down like that. And what else? 3 left. So the point that would have been here, 1 below, is 1, 2, 3 to the left. That point is right there. If you don't believe it, stick in negative 3. Negative 3 plus 3 is 0. Anything to the 0 power is 1. Negative 1 minus 6 is negative 7. So that's that point. Okay, there we go. All right, let's look at another one. Let me clean these up a little bit. Okay, a couple logarithms. So phi we got going on here. I picked crazy Greek names for my functions today. We got 4 logarithm of x minus 2. What do you guys think? What's that minus 2 do? They didn't mess it up this morning. I was surprised. I have students mess this one up quite often. What do you guys think? Oh, come on. Gotta have some courageous people in here. I heard 2, but I didn't hear. Down 2, very good. You guys got it, just like this morning. See, some people say right by 2, because I think they're thinking this. That is different. That says x and minus 2 are both inside, which would mean it's horizontal. But it didn't say that. It said, what's the only thing inside the log? That's a different question than this one. This one said the only thing inside is x. Right? So this is outside. That's down 2. Guess right. What's this 4 do? Stretch. Vertical or horizontal? It's clearly outside. Alright, logarithm shape. Should be good to go. So going down 2 isn't going to change this asymptote from being at 0. Normally it would go through 1 on the axis here, but this one, that 1 is gone. Down 2. So you're going to have this kind of a shape. Vertically stretched just means it's going to be a little steeper. Logs like to grow really slowly, though. They're like the slowest kind of growth you can have, actually, that still grows. So how steep? Well, we should probably plug in some points. Let's see. You guys, can you help me figure out some convenient points? We don't want to have to use our calculator here. What are some good things to put into phi? Let's pick three values. I'll give you the first one. You definitely want to put 1 in there, because that's super easy. Put 1 in there. What's log base anything of 1? Remember, when you put 1 in here, you're saying what, like 10 to what power is 1? 0. That's true for all powers. So it's going to be 0 minus 2 is -2, which that's the point that I just shifted down with you guys. You guys tell me, what are some other nice points that come out nice and easy? What other things could we plug in to get to come out nice here? This is one of those key skills for the final.
-1?
Nope, if you put -1, it will say error, because that doesn't exist. 5, that'll be a decimal, because log base 10 of 5 is between 0 and 1. 10. Log base 10 of 10, if I put 10 right there, what is it? It's 1. 1 times 4 is 4, minus 2 is 2. At 10, we're supposed to be 2, so if I drafted this appropriately, we'll say that's 10. What else would be nice to put in this? 100. If you put in 100, what do you get? Log base 10 of 100 is times 4 minus 2. It takes all the way until 100 for this to grow up to 6. So we'd have to go like way over here at 100 for us to be 6 high. So you guys can see logs, even when they're vertically stretched like this one, still grow slowly. Okay? So I'm not going to plot that. You guys can view. Alright, last function for us to graph today is this one, u of x. New Greek letter for you. Where's it been moved? It's a logarithm, right? It's that natural logarithm that you guys learned about last week, or whenever. Left 2. If you look at that and think left 2, you've got good instincts. You're thinking right, but it's not right. That's good, though. This is something that's going to come up more and more this year and into the future if you continue in mathematics. This has a sneaky transformation in it. You've got to do this before you say. You must factor all interior transformations. I think we've mentioned that before. I'm going to keep mentioning it this year. Hopefully by the end of the year you're good on that. All functions that have more than one transformation inside always must be factored, or you'll be fooled every time. If there's more than one transformation, and there is inside, right? We've got the minus and we've got the plus 2. That's 2 separate transformations. This graph is not shifted left by 2, it's shifted right by 2. And of course, we'll graph this bad boy in our calculator here in a sec and make sure we're all solid. This negative's inside clearly, right? Whether you look at it here or here. So that's a horizontal reflection. So let's just do a quick sketch and see if our calculator matches it. So logarithm, whether it's natural log or any other shape, you know, they all have the same kind of shape. Yep. This time is the asymptote move. Yeah. Right by 2. Logarithm shape, flip this way, and you got it. I think it's going to go through right there too. And I bet that's too steep. Logs don't grow that fast, but you guys get the idea. Yeah? Let's check it with our calculator. So any of these problems, you're definitely welcome to check with your calculator. If you rely on your calculator to do them, you're not going to learn anything. So make sure you try to do them by hand, and if you're like, oh, I wasn't sure if it was going to be like this way or this way, then check it with your calculator. That's the idea. Technology is only a tool. It cannot help you avoid things, though, so just remember that. Notice I didn't have to do anything. I didn't have to recognize anything. I just typed it straight in. Let's see if it looks like our blue curve over there. Zoom 6, I guess. Yeah, looks right, yeah.
Why does it end just right there?
That's because the calculator has a tough time with asymptotes. Asymptotes are this issue that we're going to continue to explore into calculus. So very good question, Lindsay. But basically the calculator plays dot to dot when it does it, because any machine can't hold an infinite number of information, can it? Machines always have a finite memory, whether it's 2 gigabytes or 10 megabytes or whatever. So the calculator is not doing these like we as human beings do these. We as human beings do these by what I'm teaching you, remembering the basic picture and then thinking about how to transform and move that picture around. The machine does not do it that way. The machine uses things called power series, which we're going to start looking at series next semester, but just basic, easy series. Power series are from Calc 2. The machine uses things called power series to generate a sequence of dots, and then it plays dot to dot. You can, of course, see those dots if you change it to mode. Instead of connected, you can see the dots if you do this. See how it looks like it's solid? It's because it's using a lot of dots. If you like zoom in on a part of this, you'll be able to see that they're not solid. Now, it still looks solid. It's using a lot of dots. You go back. You guys could see down toward the asymptote how you can start seeing dots here, right? So eventually it like runs out of dots, and it's like, you know what, it's just basically this. Because as you get closer and closer and closer to that asymptote, these dots get closer and closer and closer, and it becomes harder and harder and harder to compute. So it has a hard time with asymptotes for a lot of reasons. It's a good question. Let's look at one last question before we wrap up today. Just I wanted to do one more type, and then you guys can work on your stuff. So what if we have this guy? We don't have to graph this one. Let's just write down the function. Okay? So we're creating a natural log that has been transformed to these. So you guys think about this 8 up deal. Slide it 8 up. How's that going to look? Where did I put my 8? Outside. Does it matter which side of this thing? Like this? It's outside. That's stretched, not translated up. Plus 8. Now, whether you put your plus 8 over here or over here doesn't matter. Usually we're going to see it be on that side, right? What else? 3 left. Left is plus, but you got the idea. It's the opposite. So x plus 3. And then the harder part, this is the hardest transformation that there is out there in my opinion, is how do you do horizontal compression? 2 ways to think about that. 1, theoretically, I've shown you. Horizontal inside, outside. Inside. So it's opposite. You should expect a compression to be division. So since you expected it to be division, it's multiplication by 2. So this is the answer. Now, you can't put 2x plus 3 because that 2, like I said on the last example, doesn't only affect the x, it also affects the 3. So you've either got to put it outside the parentheses like I tried to show here, or you could distribute it and say 2x plus 6. Those are the 2 ways to think about it. Yeah, Miss Marie.
Is there a better way? Is either one of them?
I don't think there's really a better way. The other way that I showed you, like on your sheet, if If you didn't want to think about it more abstractly like I just did, I think abstractly is probably the better way. But I had that hint on your sheet. You guys remember I said if it's a horizontal stretch or compression, you could go f of x divided by the number, x divided by b. So if you divide by a fraction, that means you flip it, right? And if you put this 2x in, you're going to see it's going to become that. And it said to do that first, technically, so then you do the plus 3 thing afterwards. So, very good. I think the theoretical way is actually better in this case. If you learn what I've been talking about with inside, outside, what you expect, what you don't expect, that's it. There is no different thing for any higher level math. That's all there is to all functions. That's why I teach it that way. I used to do the HK method. But that's different for different kinds of functions, and it's not an overarching concept. If you learn this thing, it's done. You've learned it, period, for everything, including trigonometry, calculus, and everything else. So that's why I'm showing you it that way. And it's really only a couple things you got to remember. Okay. We'll see you next time.